everybody. Thank you very much for joining us for our second day of the Midrasha. We will start with Chapman, who will talk about the Connes embeddable problem, the second talk.
Thanks, Shai. Yesterday I was told that I didn't shout enough, so tell me to shout louder. So let's recall some things that we've done yesterday, and I'm actually going to change a bit my formalism at some point, you will see. I think it will make things clearer, because I was a bit fast at the end yesterday, so I'll try to kind of recall everything and see that we're all on the same page. So this is a recollection of what is even the Connes embedding problem. So if you have a function from some group gamma to the complex numbers, we call it a character of the group if it sends the identity element to 1. If it's tracial, so f of xy is equal to f of yx, and if for any tuple of elements, now I can talk like this, and every tuple of elements, x1 up to xn from gamma, you can construct the following matrix, whose entries are just the evaluation of the character on xi inverse xj. It will give you an n by n matrix. And if this is a positive semi-definite matrix, we call this function f a character. And we denoted the collection of all characters of gamma by just char gamma. There's a special type of characters, which are called finite dimensional. Whenever you have a unitary representation into d-dimensional unitaries of your group gamma, if you just take their normalized trace, which we are going to denote by tau from now on, then you get a character. Okay, that's basic representation theory, that this object will satisfy all these conditions. And we denote the finite dimensional characters by char subscript fine of gamma. Now, Connes embedding problem can be formulated as follows. R, for the free group F, are the finite dimensional characters dense in all characters. And we endowed the characters with the pointwise convergence topology. Okay? So a sequence of functions converges to another function if just for every coordinate they converge. It's as convergence in the complex numbers. Great. Now, yesterday I kind of glossed over, but there is a fact which is called the finite groups are stable, and you can deduce it from several sources, either from a work of Gowers and Khatami or by a work of Hedwin and Schulman, which tells you, as a corollary of this fact, you know that this formulation of Connes embedding problem is completely equivalent to the characters of a free product of finite groups being dense in the characters of free products of finite groups. Okay? So it's not clear a priori that if this is not dense here, then this is not dense here, but turns out that by stability of finite groups, it's the same. So from now on, this is the formulation that I'm actually going to tackle. Okay? So this I kind of glossed over yesterday, and I wanted to make clear.
The property of being that the finite character are dense in the whole characters is a commensurability property, namely if two groups are commensurable with each other, then one has the property and only the other.
That I don't know, but I do know that if kind of you can add, the question is, if you have a character here and it look almost like a character here, it almost satisfies the extra relations here, that's like where I'm using stability, that I can fix something here to something here. That's what I'm using here. But I don't know if commensurability is enough. Yeah, I just don't know. Again, there is something, but again, I'm not sure what is enough to just say that these things are equivalent. Here, I at least know that stability of finite groups gives you that this is enough. Refute this, and you refuted the Connes embedding problem. Yeah, I understand. I don't know what is the generality of this. I know that using stability you can deduce it. I don't know what, in which generality.
For every L or what's the...
Yeah, you need to have enough products, enough copies. I don't know, maybe you need 3 copies of, at least 3. What? Yeah, you need x to be, yeah, it's true for everything. You need enough x to be large enough, but other than that, it's just... Anyway, the interesting part is that if this is not dense here, then this is not dense here. That's the point that I'm going to use. We're going to show that this is not dense here, and from stability of finite groups, you deduce that this is not dense here, and thus Connes embedding problems is false, like has a negative solution. Anyway, that's just a recollection of the thing that we try to show in general. And the way we tackled it is via the notion of non-local games, and we gave all this motivation from physics yesterday, but I'm going to ignore it. Let's just recall combinatorially what is a non-local game. It is a quadruple of things. What are these things? A finite set X, a finite vector space over F2, so X and L are finite, a probability distribution over pairs from X, and D, which is a decision function. It takes a quadruple, 2 elements from X and 2 elements from the vector space, and give me back either a 1 or a 0, and I interpret 1 as win and 0 as lose. And this encapsulates the following kind of experiment that you can run in the real world, which goes as follows. You have a referee here. The referee can sample from the distribution mu, so it samples X and Y according to mu. It sends X to lab A, it sends Y to lab B. Then the labs do something, and we don't know what they do, but they need to output back an element A in the vector space. So just a string of L bits, that's usually how people think about this. And here, another string of L bits. And then the referee has everything that it needs to decide whether they won this round or not. It evaluates D on this quadruple, and this is the decision of the referee. So it outputs D of X, Y, A, B, where we interpret 1 as winning and 0 as losing. Now, yesterday I didn't define this notion, but I kind of used it. So let me just say this is called the correlation. So the probability, whatever the labs do, they induce some probability distribution of the following form. Given that lab A was asked X and lab B was asked Y, there is some distribution on what's the probability that lab A will answer A and lab B will answer B. Right? No matter if they flip coins or do some measurements on particles, it doesn't really matter. The behavior of the labs can be described by these conditional distributions. Right? That's the only thing that we see out of the experiment, essentially. And let's just denote this long thing as P of AB given XY. And this is called the correlation. Okay? Now, given that you know that this is the correlation that the labs use, you know what is their winning probability, right? Yesterday I denoted it as the expectation XY sampled according to mu, the expectation A and B is sampled according to POVMs, but this is assuming that they generate their correlation using a specific method coming from quantum mechanics. No matter how they do it, this is just the formulation of what is the probability of them winning a round of the game, right? So convince yourself that what I wrote here is exactly the probability that this output is 1. Great. Now let's dive indeed into quantum mechanics. Okay, let's recall some things that we've done yesterday. So the notion of a measurement generalizes the notion of a probability distribution over a finite set. So A is a finite set, and a measurement is just a function from A to positive semi-definite D by D matrices. So it has some dimension associated to it. It's a D-dimensional measurement. Let me write it here. D-dimensional measurement. It's just a collection of positive semi-definite matrices that sum up to identity. So the one-dimensional case is a probability distribution. And this is usually called POVM in the literature. And this measurement is projective if these images are orthogonal projections. So if MA squared is equal to MA. And this is called the PVM in the literature, usually. Now, we said yesterday that if you have two POVMs, M from a with outcomes in A.
MAs are supposed to be commute?
No, I'm not assuming that. This is true when this is a PVM, but I don't assume it in the POVM case. I'm just not assuming it. I don't need it at any case, at any situation. Notice that if I have a POVM M with outcomes in A, and the POVM n with outcomes NB, we gave yesterday a probability distribution, which I called sampling A and B according to the POVMs M and N. And the formula was that the probability that A, B is sampled is the normalized trace, this 1 over D trace, of MA times NB. And I said as an exercise, check that first of all, it's actually a non-negative collection of numbers, and that adds up to 1. So it's genuinely a probability distribution. And I'm sure everyone did this exercise. And the way you interpret this formula, like why is this formula, where does it come from? It comes from, again, quantum mechanics. So it turns out that when you have two particles that are d-dimensional, and the electrons with the spins were two-dimensional yesterday, but in general they can be d-dimensional in their outcomes. You can throw, and they are maximally entangled, and that's again similar to the way we thought about the electrons in the helium atom yesterday. But anyway, there is this notion of two particles being maximally entangled. You throw one of them through a measuring device M, and you get some property of the particle, which is just an element of A, and you throw the other one through another measuring device N, and you get an outcome B in B, and that's actually a way of formulating what is the probability distribution of getting A from this measuring device and B from this measuring device. So it's not out of nowhere, this formula. It comes from actual experiments.
And you're avoiding defining maximal entanglement?
Yeah, I don't need it. From now on, just when I use the usual trace, it's actually assuming that the particles are in a maximally entangled state. Yeah, that's nice, right? I don't need to tell you that this is trace of something times some density matrix or something. The fact that I'm using trace here is essentially using maximal entanglement. Yes?
But where do you take into account the dependence of the measurement of the question?
For here, I didn't do it yet. So we need to now say, how do we construct the correlations, right? So I didn't define it as strategy. Yeah, I didn't explain yet how do the labs generate their answers, right? I just said, given two POVMs, they can do this process of each measuring through their own device and do something. In a moment, I will define how do they generate their correlation. And that would be, yes, like their strategy. Okay, but I want to stop for a moment and talk about Fourier transforms. So yesterday we saw that if you have a unitary representation of F2 to the L, you can define Fourier transform. And the nice thing is that this Fourier transform is a PVM. Right? And the definition, rho hat of A, is the expectation over V's in F2 to the L of minus 1 to the dot product of A and V times rho of V. Okay, that's just a formula for it, but the important thing for us is that whenever you have a unitary representation of F2 to the L, it has a PVM corresponding to it, which is called the Fourier transform. And I want to now give you a formal Fourier transform. What do I mean by that? If you have a free product of F2 to the L's, parameterized by X and X. Yes.
These are just generality diagonal.
Yeah, these are projections. They're ones on the yeah. In some bases, these are ones on the diagonals. Yeah. Right. It's like if you mutually diagonalize because this is an abelian group, then that's what happens. Yeah. Okay, great. So the free product of F2 to the L X many times, where X is some finite set, you can think of it as generated by the following words. What are the words? Vectors from this vector space with the notation of from which copy of F2 to the L did it came, right? So let's just call these Vx's, where V is from the vector space and X is from X. You agree that these are the words kind of that we write with when we try to write this free product. Now, for every A in F2 to the L, and for every X in X, I want to write the following thing. So A hat X is just the expectation over all V's of minus 1 to the dot product between A and V of Vx. Now you should shout at me and say, okay, these were group elements. Here, what am I defining? I'm defining some linear combination of group elements, but that's okay, right? This lives in some natural algebraic object called the group algebra. And it's true that our characters were not defined on the group algebra, but you can just, whenever you have the function on the group, you can just extend it linearly to the group algebra, right? So from now on... Yes, thank you. Yeah, I wrote here gamma. I should have written here the free product. Thank you. But that's okay, right? Like we have this notion. So from now on, for every f character of the free product of f2 to the L x many times, I will just denote by P of f the correlation. A and B are the outputs given x and y, which is the character evaluated at A hat x, B hat y. So you agree that at least this is some complex number, and again you can check that this is genuinely a probability distribution for every fixed x and y. You will get here a probability distribution, so it indeed induces such a correlation. Great. Now I can define, so these are, for your question, Amnon, if I think of their strategies as coming from characters, this is the way they can answer. So now I can either give them the ability to use infinite dimensional characters, or any possible character, or just the ones coming from the smaller set of finite dimensional characters. And that's what we're going to do. So the quantum value of a game G is the supremum over all finite dimensional characters. So f in car finite of the free product of f2 to the L x many times of the value of the game when you use P of f. Okay? So I said that if they generate their answers according to this correlation, this is the winning probability. So this is just the maximal winning probability when they use finite dimensional characters as their strategies. And you can define the bigger number, which is usually called the quantum commuting value, and I will not elaborate why it's called that way. This is the supremum over all possible characters, and not only the finite dimensional ones, of the same thing. The value of G when using the correlation induced by this character. And clearly, just because we use a bigger set over which we take the supremum, this thing is larger or equal to this thing. Okay? Yes?
You told us that f you find only on the group, but you enter inside something little...
But that's what I said. Like, whenever you have a character, how do you extend it to the group algebra? Just extend it linearly. It's like giving me the value on a base and then just extend it linearly, right? It's very similar. Okay? Yes?
So just to say, in my own, because
Yeah.
any quantum operation is just applying some POPM, you can express any quantum strategy as a character, as a PF of some kind.
Yes, and but here I'm using very much the fact that I fixed the state, right? Like, I fixed the state. I don't need to explain to you each time which state am I talking about.
What state?
The maximally entangled one.
State, the
Yeah,
POPM, it's in EPR.
Yeah, not the generalization of the EPR term, but yes. Yeah.
Mm-hmm.
The maximally entangled state. Great. So we have these two numbers, and just note, let's move this to the side, but let's still see the Connes embedding problem. The Connes embedding problem told us that if it's correct, the characters are dense here. Now, this formula, maybe I shouldn't have moved it. This formula induces a continuous function from the characters, okay? When you evaluate like val g, this thing, val g pf is a continuous map from the characters to the numbers between 0 and 1 actually, right? So if this set is dense here, taking the supremum over a dense set gives you the same number. So in particular, just a corollary, yes to Connes embedding problem implies that the quantum value of a game is equal to the quantum commuting value of the game. Okay, great. So we have that. Now I just want to say something because actually I prepared it before and also Amnon asked it now. So let me do a quick analysis of finite dimensional strategies. So we remember that in this case, in the case where things come from here, they come from unitary representations.
Sorry, Mika?
Yes.
So yesterday you were mentioning Tillotson problem. Is that Tillotson problem?
So actually, Tillotson problem asks whether the correlations, the PFs. So it asks whether the PFs coming from the finite dimensional ones are dense in the PFs coming. But clearly, if they are dense in that sense, you deduce this. So this is a weaker than Tillotson. Maybe it's even equivalent. Maybe, I don't remember. Like maybe this is already equivalent. But he asked originally about the correlations. Other questions? Remarks? Okay. You will have many opportunities to stop me, so feel free. And I want to write it very quickly. We said the finite dimensional character is just the normalized trace of rho x for some finite dimensional unitary representation of the free product of f2 to the L to UD. And I just want to say, okay, you want to give me a unitary representation of free products of f2 to the L. It's the same as for every x in x, give me a unitary representation of f2 to the L. So it's the same data as just giving me for every x in x a unirep of the same dimension. That's important, rho x from f2 to the L to UD. And then the way that PFAB looks like, AB given XY, is just a sample A and B according to the Fourier transform rho x and rho hat y. Okay, so that's how I defined it yesterday, but I wanted to just clarify that that's the notation that I used yesterday, and now I use a more correlation notation because I think it kind of made it more clear. Great. Let's move to computational theory and decision problems and do some theoretical computer science. Any questions up until now? Because now I'm moving to a completely different topic. Yes?
Just that
as I like. What else?
just to make sure, in your previous definition, or the definition of the value, you could have packaged the gain itself.
I could have packaged what?
Like in just the last word you wrote down, not this one.
Here?
No, the previous one, the
On the last word.
GPF.
Val GPF. Here. The way I define this?
You could have like averaged inside the group algebra A hat X to get a single group algebra element for which you evaluate the trace on to find the value, right?
No, because I multiply them with, I don't understand. I need to calculate each PAB given XY independently. And for each one, it requires me to evaluate the character on some group algebra element. But I don't see now how, yeah, you're right. I can push these things in also.
You can
Right?
average according to mu xy, A hat X, and B hat Y.
Yes, I don't know. Like that's the question of like some linearity. You are asking some linearity question. Maybe I could have done it. Yes. Yeah.
Never mind.
So it doesn't really matter, right? Yeah.
Yeah.
Okay. Other questions, remarks? No. Let's move on. So now I want to talk about decision problems. Decision problems. So what are decision problems? If I have a subset of finite bit strings, so this is the free monoid generated by 0, 1, it's just all finite bit strings. This is called a language. And every language induces the following decision problem given a bit string is X in the language. That's a decision problem. And we never think about bit strings. We always think about the bit strings as encoding some combinatorial object. So actual examples of decision problems are always of the form I give you a combinatorial object, decide something about it. So given Turing machine, does it halt on the empty bits, on the empty input, for example? Given a graph, is it free colorable? Given a finitely presented group, is it trivial? So for example, for the last part, you need to somehow first decide how do you encode a finite presentation of a group, but once you do it, given a bit string, I can decide, okay, this is a finitely presented group, is it trivial or not? That's the type of question. And these are nice decision problems, but I want to talk about a more generalized setup, because that's the setup that we will need for MIP star, which is called a gap problem. So what is a gap problem? So now instead, here in the decision problem, just for every combinatorial object, I'm telling you, yes, it's good, or no, it's bad. In a gap problem instead, I'll give for every combinatorial object some value, some number associated to it. So I'm giving you some function, which we always call the value, from the combinatorial objects to some number between 0 and 1. It can be from some other span, but let's normalize and put everything between 0 and 1. And then you have some new decision problem, which is called the promise problem, associated to this. Given a combinatorial object X, is the value of X 1, or the value of X is bounded by some number S, which is strictly smaller than 1. So in this promise problem, there is some parameter here S, which is called the soundness, and I care about distinguishing between these two cases. Now you should tell me, okay, but maybe I will give you some combinatorial object X whose value is in between S and 1. The answer is, I don't care. In this case, do whatever, say yes or no. I want you to be correct only when either the value is 1 or when the value of X is far away from 1. So I'm promising something to you about the inputs that I'm giving you. That's why it's called also a promise problem. Let's see an example. So what would be the free colorability value of a graph X? Okay? It will be the supremum over all possible colorings, free colorings of the vertices of X. So I just give for every vertex a color. And then I'm counting how many non-monochromatic edges are there in the graph. So all the edges that are good with respect to this coloring, and I divided it by the total amount of edges in the graph. And you agree that if the graph is free colorable, then this is just 1. There is some coloring that gives you just 1. But if the graph is not free colorable, there is the best coloring out of all of them that kind of has the least amount of monochromatic edges. Right? No, I think I wrote it such that these are non-monochromatic edges, and I think I wrote it correctly. But anyway, what is the promise problem in this case? So this is, let's call it free cal 1.99. This is the decision problem given a graph. A graph, is it free colorable, so if the value is 1, or does every coloring have 1% monochromatic edges? So notice this seems to be a much easier problem than the original free coloring problem. So I'm promising to you that I will never give you a graph which is not colorable, but only by one edge or something, that you can remove one edge and suddenly it becomes colorable. The graph that I'm giving you is either free colorable or very far from being free colorable. That's the way we should think about it. Hmm?
At least 1%.
Every coloring has. Does every coloring? Should I write have or has here? Have is okay. Okay. No, at least does every coloring have at least? Yes, at least. Thank you. 1% monochromatic edges. Now it's okay. And like a fundamental, quite amazing theorem called the PCP theorem in theoretical computer science says that actually this problem, which is on the surface seems easier than regular free coloring, is also NP complete. So it's also as hard as the original free coloring was. So it's not really an easier problem. And that's the deep theorem. Now, what is MIP star? So that's the kind of promise problem of the day. Given a non-local game G, is its quantum value 1 or its quantum value is bounded by 1/2. So we define what is the quantum value, so we at least have this parameter. Now you can tell me, wait, can I encode the non-local game as a bit string? At least when the distribution mu is rational, clearly you can. So let's recall what is a non-local game. Where is the what do I need to encode? So I need to encode two finite numbers, x and l, right? I need to encode this function from a finite set to a finite set. Clearly this is encodable as a bit string. And I have this probability distribution. So as long as it's rational, I can encode it, right? So this problem parses as a promise problem. This is not the original formulation of MIP star. Let me just clarify this. That's kind of the easiest way of me to convey what MIP star is trying to say.
So MIP star, but you're saying that it is equivalent for this property for all local games, and now you view this as a property of a given local game?
This is a decision problem. I'm giving you an input, which is a non-local game. Distinguish between the case where the value of the game is 1 and the value of the game is bounded by 1/2. It's a decision problem,
I
right?
understand. I'm just asking whether MIP star is the statement that every local game has this.
No. MIP star is a computational task. It asks you to compute something. Now the computational problem or the complexity theoretic problem is how hard is it to solve this problem? Similar to before, I give you a graph. How hard is it to check if it's three-colorable? This is known to be as hard as any language in NP, right? This Turing machine, does it hard? This is Turing's halting problem. This is known to be undecidable. There is no algorithm that can perform this computational task in finite time. How hard is this task? That's the question. And it's not clear on the surface how hard is this task. Yes?
Yeah. Could you clarify exactly where the complexity, it seems to me in the end you don't use complexity.
Here, I defined it without any complexity, and we maybe will see some complexity in this following 25 minutes, and maybe not.
I mean,
The way I defined MIP star is complexity-free. It's a decision problem.
so maybe the proof is complexity-free. The techniques use complexity?
Yeah, at some point you need to use, I will try to get there.
Okay.
It turns out that the paper that we talked about and I remarked that last time is that this is equal to RE, namely this computational task is actually as hard as this computational task, and Turing taught us that this is undecidable, so this is undecidable. There is no algorithm that can perform it. This is a computational statement. There is no complexity here. But quite an amazing work of Andrew Marks and Najidi and Henry Yuen showed that any RE result is equivalent to some claim that does contain running time constraints and something like that. So this is actually the setup of what they call compression in the MIP star paper is actually a very general thing. It's not a singular phenomenon. But I'm not sure hopefully I will tell something about compression today. But let's try to move towards this. Okay, great. So I'll write here. Hopefully I will not hate myself for removing this. Let me try to keep the value definition. So let me give you a short theorem. At least the second part of the theorem is due to Navasquez I hope I'll write their names correctly, Pironio and Asin from 2008. In the literature, it's known as the NPA hierarchy because of their initials. And what it says is that given a non-local game, G, there are two algorithms. So there exists an algorithm which outputs an infinite sequence of numbers. So it will start outputting the numbers one by one and it will run forever. Alpha 1, which is smaller or equal to alpha 2, which is smaller or equal to alpha 3, dot, 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 such that the alpha i's converge from below to the quantum value of the game. And there is another algorithm which outputs beta 1 larger or equal to beta 2, larger or equal to beta 3. So this is a decreasing sequence such that beta I tends to the quantum commuting value of the game. Let's see that we believe this thing. Okay, does anyone have a suggestion? How would you construct a sequence of numbers that converges from the low to, where is val q? I don't have it anymore. No, I don't have it anymore. Sorry for that. Yeah, exactly. So fix a dimension, take some epsilon net and make the epsilon smaller and smaller as the I goes to infinity inside all representations. Okay, this is possible. And then just take the supremum. Okay, so this alpha I is just in the I-dimensional representation, take a 1 over I net inside these unitary representations. It's a finite set. Just evaluate the value for each one of these. Take the biggest thing you found up until now. Maybe because of the epsilon net that you chose, this alpha I minus 1 would be bigger than alpha I. But as long as you take the biggest number I saw up until now, you will give a non-decreasing sequence that actually gets the quantum value. How do you get from the up part? So this is not the NPA hierarchy. This is the NPA hierarchy. So think about the definition of a character. This is still on the board, right? You want to give me the supremum over the value over this thing. Now, if you check here, and you don't care about all possible x1 up to xn, just give me a finite set, okay, which always includes 1, the identity of the group. You will get a positive semi-definite matrix with some extra conditions on it that needs to optimize some linear functional, which is the value. This is called a semi-definite program. Like people in computer science study this stuff. And you can calculate the optimum of a semi-definite program. And notice that the more values that you add here, the more restricted is your semi-definite program. So you will get a worse optimum. So the beta i's will only decrease. What are they? Yep. So you do a semi-definite program with restriction only on a few elements, and then you restrict on more elements and more elements, so you get a more restrictive semi-definite program. And in the end, you will kind of encapsulate all possible restrictions in the infinite case, and you will converge into the quantum commuting value. So that's called the NPA hierarchy. Yeah? You need the starting set to contain all the elements that actually are checked in the characters. Like you will check, I need the starting beta 1 already needs to contain some large enough set, but then I just can add one by one all the elements of the group, and it doesn't matter the order in which you add them. Yeah?
So this would work for any group, or you use the fact that your group is locally finite?
I think I used the fact that my group is countable, right? But other than that, I don't think I used anything else. Yes?
Sorry, can you repeat that again?
I essentially gave you now an outer approximation of the characters. How do I give you something which is weaker than a character? I don't force you to have all these properties for all the inputs of the groups. Just restrict yourself to a finite set. Let's call it B. It's a finite set inside the group. And now just on this set B, use it as x1 up to xn. You will have that these values are a semi-definite matrix. And they have this property, and it has this property. And you need now, under these conditions, functions now from B. I forget about the rest of the gamma. Just functions from B to C. That's a finite dimensional vector space, right, over the complex numbers. So I essentially kind of reduced your case into a polytope in some finite dimensional space. That's what happens here, actually. And this is kind of, when you lift things back up to functions from gamma to C, you actually have an outer polytope approximation. Sorry, convex body, right, because it's a semi-definite program, right. So outer convex body approximation of your characters, yeah. Okay, great. Notice what does it tell us. So let me just pictorially, everyone always draw this picture, so let me draw it as well. So if this is the quantum commuting value, which is a priori larger than the quantum value, this one gives me some thing that approximates from below, and this 2 gives me something that approximates from above. Now, what does the Connes embedding problem tells me? It tells me that these lines are the same, right? In particular, it tells me that the picture is actually like this. This is the same line now. So the upper approximation and the lower approximation will be arbitrarily close, right? At some point, they will be arbitrarily close. In particular, they will be smaller than 1/2. So if you run these two algorithms in parallel, at some point this gap will be lower than 1/2. But this means that you will for sure know whether the quantum commuting of the game is either smaller than 1 and then it will be 1/2, or larger than 1/2 and then it will pop up to be 1 because I'm giving you a promise problem. That's the nice thing about the gap problem. So in particular, Connes embedding problem, so let's write it that way. Connes embedding problem, that's a corollary, implies that MIP star is decidable. And by decidable, I exactly mean there is some algorithm that can decide this problem in finite time. Will always give me an answer in finite time. I have no bound, no complexity, no running bound on the time, but at some point it will do it.
Can you explain again why it does not need to be decidable if this is the picture?
This gap can be larger than 1/2.
And then.
Yeah, I will. Maybe this will be stuck at 1, and this will be stuck at things lower than 1/2, and I will never know whether this. Yeah. If the gap between these two values is larger than 1/2, this can be undecidable.
But if the gap is a quarter, then you say.
Then I will always be able to decide. Yeah, yeah, yeah. If for some reason the gap was always smaller than 1/2, then I will always be able to decide.
Much less than Connes embeddability.
For deciding this, you're saying? Yes, yes. If I had some bound on the gap, then some gap problem would be decidable. That's true.
And the half is not magical.
Yeah, any constant between 1 and 0 holds, yeah.
So you could formulate this as some invariant that finite dimensional. This is the invariant which shows that finite dimensions cannot approximate infinite dimensions.
Okay, so by definition, this is something coming from finite dimension, this is coming from infinite dimension, and this distinguishes the finite from the infinite, indeed. But that's exactly what we're trying to do. We have two convex sets, right? Yes. The characters and the finite dimensional characters, and we try to separate them using a functional. And the value of a non-local game is exactly a functional on these convex sets. So it's kind of the natural way of distinguishing between two convex sets using functionals, and the value is exactly the functionals. Okay, let's keep on. Let's keep on. As we said, this is not true. So what did G, Natarajan, Vidick, Wright and Yuen showed us? I'll start erasing stuff, okay? Hopefully, maybe I'll use the last board and then I'll erase stuff. Anyway, once I erase stuff, Doron cannot see the board. So what did G, Natarajan, Vidick, Wright and Yuen have shown in 2019 that MIP star is actually as hard as the halting problem, as hard as the halting problem. And thus, It is not decidable, and thus Connes embedding problem. Maybe I should have written here yes to Connes embedding problem. And thus Connes embedding problem has a negative answer. Okay? Now the interesting question is, how do you prove this? So first of all, what does it even mean to be as hard as the halting problem? It means that whenever you have a Turing machine, I can translate it into a non-local game, G, such that if the Turing machine halted, the value of the game is 1. But if the Turing machine does not halt, the value of the game is at most 1/2. That's what you're trying to do. Okay? Now, yes. So they don't do it in a way which is kind of very easy to describe. Now I need to stop and think for a moment. What do I want to say about this? So, yes. So how do you do this? How do you show that a non-local game is doing this? You need what's called a compression mechanism. And that's what I said that Andrew Marks with Najidi and Yuen have shown that is actually, whenever you have a reduction to the halting problem, you can essentially describe it as a compression result. So what is compression? This needs to run in polynomial time, okay, or in some bounded time with respect to its input. So it's an algorithm, compression, that gets as input a non-local game G and gives you a new non-local game, G prime. And this G prime has a few properties. So I'm going to state it in a non-rigorous way, but that will give you all the correct ideas. So what are you trying to do when you compress a game? You try to make it smaller. What does it mean to make it smaller? One way of thinking about it is just making x and L smaller. So the size of x prime, so this is G prime is x prime f2 to the L prime mu prime d prime, okay? And this was x f2 to the L mu d. And the first thing you want is that x prime and L prime are polylogarithmic in the size of x and L, and polylogarithmic in the size of L, respectively.
All right, so this brings in complexity.
So first of all, this needs to run in some bounded running time.
I'm just curious whether this polylogarithm is actually essential for the proof. In other words, is that kind of...
You don't need exponential compression. This compresses exponentially. You can use weaker compressions, but that's for surely what they prove.
It's a philosophical question.
This needs to run in polynomial time. You can have lower gains and still deduce the MIP star is equal to RE, so still deduce this work. But let me just say, what do you expect from the output of this process? So you need some process that takes a non-local game, gives you a new local game, such that the size parameters of the new local games are much smaller. But you need to pay a price. What is this price? The entanglement. So, okay, if the value of the original game, G, was 1, then the value of the new game is also 1. And you want to write something, if the value of the original game was at most 1/2, then the value of the new game is at most 1/2. I want to give you some stronger assumption, okay? So let me, for a moment, just talk about entanglement bounds. So, what is the entanglement of a game with respect to some parameter nu? This is a number between 0 and 1. It is the minimal d in the natural numbers such that there exists a finite dimensional strategy of dimension d, which we will call F. Remember, our strategies are characters of the free product of F2 to the L. And we said that the final dimensional strategy is that's the unitary representation of this group, right? Remember this old stuff. So F is the character associated to this d-dimensional strategy. So we have such a strategy such that when you check how good does this strategy play out in the game, it is at least 1/2. So what is the lowest dimensional strategy? What? New. Thank you. Sorry. New. Here, new. Later, 1/2.
Dimension of the character F?
Yeah, exactly. That's the dimension of the unitary representation from which you generate the character F, such that when you play the game, the labs win with probability at least new. So you agree that, I don't know, for some low numbers, it can be already one-dimensional. Maybe I have a one-dimensional strategy, but once I pass some number, maybe I need already two-dimensional strategies to win that good, and maybe I need three-dimensional strategies to win even better. So clearly, for every kind of bound on how good do you want to play the game, there is some smallest dimension. Notice that this can be infinity, right? So I wrote here mean, but that's a lie. Like it's kind of, it can be, maybe you can never win with a finite dimensional strategy as good as 1/2, for example. That's part of what we're trying to show. And what the compression gives us is actually that the entanglement needed to win the game G prime with probability at least 1/2 is larger or equal than the minimum between two things. One of them is the original entanglement of the game G to win with probability 1/2, and some number that gets bigger the bigger the original game was. So let's just call it 2 to the power of the description of the game G. So again, you remember that we encode our games G as bit string, so this is just some number which is associated with how big is the original game. So you can also write here 2 to the size of the X, this size X set, that's also enough.
But the price that you mentioned is this dimension
This is
of
the
character that now will...
Right, like the trade-off here, the way that people think about this result is that there is some trade-off between how big is the description of the game and making the game smaller, but somehow to win the game is actually harder. Notice that what we get here. And you can see where in the proof it happens that actually you generally trade dimension bounds with the description length at some point. So it's kind of crucial. And it turns out that this is enough to deduce RE completeness, and that's like these types of results are actually equivalent to RE completeness. That's the result that I mentioned. Yeah.
Sorry, I'm getting a bit confused. So this inequality, E of G prime bigger than E of G, what inequality, what implication does it give?
So clearly it means that the value of G 1/2, if the value of G was smaller than 1/2, this is infinite, and then this must be infinite. So you can clearly deduce like that it preserves the value, but it gives you something extra. Like I'm saying, this runs in polynomial time. So the way you actually now you need a reduction, right? What does this say? You start with a Turing machine M, and you want to translate it to some non-local game GM. And the way that you do it is you don't really give me a specific game, you give me an infinite sequence of games, first of all. And actually, I said that this is not a rigorous way of writing compression. Compression works on infinite sequences of games, actually, encoded as a single Turing machine. So there is like the more correct way of formulating everything here. But in this reduction, this thing kind of, in its definition, it both runs this Turing machine for some time, and also compresses itself. So there is some, like in computer science, there are functions that can call themselves. So there is some self-reference. So kind of GM is defined already as the compression of GM inside. It's kind of a nested thing, but only if the Turing machine does not halt. So as long as the Turing machine runs, this thing will kind of compress itself. Yeah, I'll stop in a moment. This Turing machine will call itself, and somehow the way you deduce that this was larger than 1/2 is that it calls itself, so somehow this value is equal to this value. If if part of the definition of GM is calling compress of GM, right? So what is the lower bound on this? This is equal to this, but this is 2 to the G. But this is also equal to G double prime compressed twice, which is also equal to G triple primes. And this makes this 2 to the G, 2 to the 2 to the G, 2 to the 2 to the 2 to the G. So the lower bound on this becomes infinite. And that's how you deduce that when the Turing machine never halts, it kind of compressed itself infinitely many times, so the lower bound here is infinite. So you cannot win the game with probability bigger than 1/2. So that's what happens in the proof at some point, in a rigorous way and not in this hand-wavy way. Let me stop here and if you have any questions.
Any questions?
So have you got a write-up of this, which is minimally computer science?
A write-up which is what?
Minimal involvement of computer science. It does seem that there's a problem here with communicating between two communities.
Yeah, sure. So we wrote a paper which proves something slightly stronger, which also covers some other open problem called the Aldous-Lines conjecture, which I didn't talk about in these two lectures. That's my work with Alex and with Louis Bowen and Thomas Vidick, who's also here. And when we wrote our reduction, I wrote most of it on the level of actual writing, and in my mind, I wanted every graduate student to be able to read it, math grad student. So I think every math grad student can open this paper and understand all the details. That I can assure you. It's 200 pages long, so I'm not saying that it's a short read, but it's a possible read for a mathematician. Yeah.
Michael,
Yeah.
can you explain in a nutshell maybe the point of the running time and
Think about it. If this game compresses itself and then runs the compression.
Yeah.
You want both the compression to run fast and also after you compress, running the compressed thing to both the compression operation and the thing that is compressed need to run fast.
Why do I need to run fast?
Okay, so now you need to
Like it has to do with the halving problem, you mean, or
so it's not very clear the way I defined it, why it's important, but it is important. The way you define GM, you need the compression to have some bound on the running time, which is of this form. Like you can actually have something which is, if this thing runs exponentially fast, only in exponential time, this still works if you choose the kind of category of non-local games in the correct manner. So you don't need really polynomial time, but you need some like bound on the running time, which is meaningful, and then you can do this operation. And you don't see it from the way I defined it, yeah, but you do need it. It's in this self-reference thing. Thank you, everyone.